Hey guys, and welcome to today's tutorial where we'll be deploying our own LLMs using the powerful combination of Ray, AWS EKS, and Kubernetes. So you might be wondering, why did we choose Ray for this endeavor? Well, Ray is not just any AI framework, it's actually the powerhouse behind ChatGPT itself. In its case studies paper, Anyscale lists companies like OpenAI amongst Uber and Shopify as users of Ray. It's a rock-solid choice for deploying your very own LLM because it provides the compute layer to scale applications without actually becoming a distributed systems expert yourself. In this video, I'll go through the end-to-end process of deploying a distributed Ray Python server using Kubernetes, covering both local Kubernetes deployment using Kind, as well as a cloud-based deployment on AWS using EKS, with ingress to serve your very own LLM. For this example though, I'm using Flan T5 from Hugging Face, but you can use any LLM that you'd want to. By the end of this video, you should be able to hit an endpoint with a prompt and get back your response. So let's get started. The GitHub repo, for those who want to follow along, is linked to in the description. Let's jump straight into the code. So RayServe integrates with FastAPI, a versatile web framework for building RESTful APIs. This integration allows us to define a serve deployment using the serve ingress decorator wrapped around a FastAPI app. Now, if I send over a request to /flan t5 route, this will be routed to the LLM method of our deployment here. Above the API class, we've also defined a prompt model using Pydantic that will be used to pass the request body with the required prompt field. Defining a model like this helps us validate the data that we get sent over to our API and also helps us generate a schema for the API using the OpenAPI standard. We take the prompt and pass it to the generate method of a Flan T5 serve deployment. Deployments are a central concept in RayServe. A deployment contains business logic or an ML model to handle incoming requests and can be scaled to run across an entire Ray cluster. So let's take a look at this Flan T5 deployment. To define a deployment, we use the serve deployment decorator on our Flan T5 Python class. Simply put, our base class here uses the pre-trained Flan T5 model from Google for language tasks. These lines in the init method load the model and the tokenizer corresponding to the Flan T5 model. The tokenizer is responsible for converting text to a format that the model can actually understand. In our generate method, the prompt is tokenized and converted into a suitable format for the model. The model's generate method is then called with the tokenized input. It generates a sequence of tokens in response to our inputs, and the generated tokens are then decoded back into a string and returned. So let's see if all of this works. Running the base class and simply asking what is the meaning of life, we get something back. We can then start the Ray server locally using RayServe followed by our import path. So in this case, it's serve run app main app. And we can see that our server starts running on port 8000. Testing the endpoint in Postman, we can see that our Ray server is up and running and responding how we would expect it to. For RayServe, it is recommended in the docs to deploy it in production on Kubernetes, with the recommended practice to use the Ray service controller that's provided as part of KubeRay. This integration brings scalability and some other operational niceties out of the box. Our journey today though begins with creating a local Kubernetes cluster using Kind, a fantastic tool for spinning up Kubernetes clusters within Docker containers for testing. To start, we create a local Kubernetes cluster. We then install the KubeRay operator via Helm, and then we can verify that our KubeRay operator is running. So if I get pods here, the container is still creating, but after a couple seconds, the KubeRay operator gives us a status of running. And next, we configure the Ray service custom resource to manage Ray clusters and RayServe applications. A core part of this is creating a YAML file for the CR configuration, specifying critical details like Docker images, ports, and other settings. To package and serve your code in a custom Docker image, you need to extend the official Ray Docker images with your dependencies and package your serve application. The Ray project organization maintains Docker images required for Ray. For example, our sample app here uses a Docker file extending the Ray project /Ray image. Sometimes though, you may not want to push an image all the way to Docker Hub, and instead you just want to run it locally with a pod based on an image that you've built on your PC. To do this, you'll need to do two things. Make sure our Kubernetes cluster can access the image, and then set the image pull policy to never in the Ray cluster config. If you're also using Kind as a local Kubernetes playground, Docker images can be loaded into your cluster nodes with the command kind load Docker image. To manage the Raise Serve application locally, we can create and update a Raise Service custom resource by applying this YAML using kubectl apply. Once the Raise service is created, you can monitor its status via standard kubectl commands, which will provide insights into the health and readiness of the application. Here, we select the pods using labels to see if everything is deploying as we want. When the Raise service applications are healthy and ready, KubeRay creates a head service and a Raise serve service for the Raise service custom resource. For example, here we have Raise service LLM head SVC and Raise service LLM serve SVC. Note that the serve SVC is the one that can be used to send queries to the serve application. You can access the dashboard through the head node though. For interacting with the server locally, we set up port forwarding. So here we forward the dashboard port to localhost and we check the serve page in the Ray dashboard at localhost 8265/serve. For querying the Ray service locally, we can also set up port forwarding and access the service directly. So here you can see we can easily hit the FLAN T5 route again and get a response that we would expect. If you're ready to scale up and deploy on AWS with EKS, there are some extra configurations to keep in mind as compared to deploying locally. First off, creating an Amazon VPC with subnets and an IAM role for your EKS cluster is a crucial step that you can just follow the AWS docs for. Don't forget to set up permissions for essential services like ECR as well. Add the cluster in the UI after the basic setup is done. Choose the cluster service role we just created, as well as those VPC and subnets we created. But otherwise, the rest of the options can be left as the defaults. In the review tab, you may also want to take a note of the subnets because we're going to need them for the ingress later. Creating a kubeconfig file is the next order of business to enable communication between kubectl and your EKS cluster. Create or update a kubeconfig file for your cluster by running AWS EKS update kubeconfig. For node creation, you have two choices, Fargate or managed nodes. In our case, we opt for a managed node group, carefully specifying subnets and node IAM roles that we had created earlier. You may also want to create a GPU node group for Ray GPU workers. You can also add ordinary Kubernetes taints to prevent scheduling CPU pods on these GPU node groups. Deploying on AWS also means creating a private repo in ECR for the Ray LLM Docker images. We build these Docker images locally and push them up using the provided commands. When referencing an image from ECR in our YAML custom resource files, we also need to use the full registry repo tag naming schema for these images, so make sure we keep a note of that. Also, to use these ECR images with EKS, make sure that the EKS worker node IAM role also contains these IAM policy permissions for ECR. Next, we need to update the custom resource YAML to reference this brand new image, and also we need to remove the image pool policy never that we added for local images. After deploying the Ray service the same way we did when we deployed locally, monitoring its status is quite easy. If we get the services, we can successfully see our Ray service LLM serve SVC. Running the same port forwarding as before now, we're able to hit our root route, but now our Kubernetes cluster is actually hosted on AWS. Using port forwarding is okay for dev, but we need to do a bit better in production to be able to access it by configuring a Kubernetes ingress to access our cluster from an endpoint instead. The first step to doing this is to follow the installation instructions to set up the AWS load balancer controller. This controller runs on the worker nodes, so it needs access to the AWS ALB APIs with the associated IAM permissions as well. We also need to set up the ALB ingress YAML. We need to make sure that the subnets annotation includes at least 2 subnets, and that one AZ has at most 1 subnet. In this example, we also need to select the public subnets as well. We also need to set the name of the head pod service to what we want to direct to, and in this case, that's the Ray service LLM serve SVC. We apply it and we check the status of the ingress. You should now also be able to check the application load balancer that's been spun up for you on the EC2 console. The name of that ALB should be along the lines of K8s, defaults, and then a name. We wait for it to fully be created, and then we can use the ALB DNS name to interact with the newly deployed Ray API. Hitting this brand new endpoint, we can see that we've successfully deployed our own LLM on a distributed Ray server using AWS EKS. Although admittedly this LLM does give some quite quirky responses, the method of deploying to Kubernetes should be very similar for other LLMs. And there you have it, the bare bones of deploying a distributed Ray Python server with Kubernetes onto AWS EKS. Admittedly, I missed out quite a lot, like persistent logs and defining the scaling laws, so leave a comment if you'd want to see that in a part 2. Before we go, be sure to check out the references provided in the video description for further reading. I've also put a link to my personal wiki for a lot of the commands that you've seen here and extra details of deploying your very own LLM. Thank you for joining us on this journey. Don't forget to explore the code on GitHub, that's also linked in the description. If you found this video helpful, please consider liking, sharing and subscribing for more tutorials like this. Peace.